Hello everyone, I welcome you to the lecture Fuselage Design of the course Unmanned Air Vehicle Design. Today we're gonna see about what is fuselage and how the fuselage is designed and what parameters play an important role in designing this fuselage. What is a fuselage? What is UAV fuselage? How this fuselage is different from conventional fuselage? Basically, when we talk about fuselage in conventional aircraft, it is the portion of the aircraft where we accommodate passengers, cargoes, and other accessories. But coming to unmanned aerial vehicle fuselage, it is the third component that considerably impacts the unmanned air vehicle aerodynamics. Its primary function is to accommodate or house the payload and autopilot system. Payload is defined as the useful load an aircraft is intended to carry, like sensors, cameras, and other accessories. For non-military UAVs, the payload typically includes items such as autopilot system, measurement devices, sensors, and other communication equipment. When it comes to commercial, it is totally dependent upon the mission which it is carrying. For example, an unmanned air vehicle which has intent to carry some logistics of 1 kg or 2 kg depending upon its total maximum takeoff weight, it will carry that logistics accordingly. For military unmanned air vehicles, the payload can include such as rockets, missiles, and bombs. It is important to note that fuel is not considered as a payload. When we take the maximum takeoff weight MTOW, we include empty weight, payload, fuel weight, right. This empty weight is structural weight, this is payload. Payload, whatever mission it is having, it will carry according to those missions. Then fuel weight, right. But in this unmanned air vehicle, we don't consider this cockpit plus crew weight. This is crew weight, crew and cockpit weight. So we don't have any crew here in the unmanned air vehicle. So this is nullified to 0. We have only empty weight, payload, and fuel weight. So fuel weight is a different entity. So sum of this empty weight plus payload plus fuel weight is to maximum takeoff weight. Sum of the weight is maximum takeoff weight. And many unmanned air vehicles are having electric propulsion. In case of electric propulsion or electric motors, power suppliers, that is added into this empty weight. So we'll have only empty weight plus payload. Beyond the primary payload and autopilot system, the fuselage is also highly likely to enclose other major components and systems in order to help in reducing the aircraft drag, which includes landing gear, engine, fuel system, and power transmission system. Avionics are also housed within the fuselage. The entire avionics system is being placed inside the fuselage system such that it is completely streamlined. As in unmanned air vehicle, there is no human factor, right? It's unmanned air vehicle, which is it will not have any human involving in the flight. human will be controlling the flight from the station using a RC channel. Right? So since UAVs do not have humans on board, the design does not include a cockpit or cabin, and therefore the human factor is not a consideration in the fuselage design. While a pressurized cabin is placed in most of the conventional aircraft, but here in unmanned air vehicle, often it is not required. A pressurized compartment might be sometimes necessary if a certain avionic or payload components do not operate efficiently at low pressure. For example, the Global Hawk's aluminum fuselage includes pressurized payload and avionics compartment to house heat generating avionics. Pressurized compartments are specifically required for convection and conduction cooling techniques. Radiation heat transfer can work in a vacuum or low pressure, but it is not effective for cooling high temperature sensor. The key design expectations during fuselage design. During the design process, several expectations are recommended for consideration. First being low weight. As the aircraft will have low weight, as the unmanned air vehicle will have low weight, it will need low power for the takeoff. The required power will drop down. The second one is low drag. The fuselage drag typically contributes 30 to 50% of the aircraft's zero lift drag, that is CD0. Positive contribution to lift generation. The fuselage can be aerodynamically designed to provide as much as 20% of the total lift through in a basic configuration. It usually produces about 5% of the aircraft's lift. It has to be externally symmetricity. Safety against environmental hazards such as lightning has to be considered. Thunder strikes, lightning strikes, these all has to be considered while designing the fuselage. The major design parameters which are considered in the fuselage design includes, during the design process, the two major fuselage parameters must be determined. First one is length of the fuselage and second one is diameter of the fuselage. Both the fuselage configuration and these two parameters are dependent on various design requirements. Drag reduction is a crucial aspect of unmanned air vehicle fuselage design, significantly impacting the aircraft's overall aerodynamic efficiency. The sources highlight several key points regarding drag and its reduction. Impact of fuselage design. The fuselage is a substantial contributor to the aircraft's overall drag. Profile drag is one example for this. Specifically, fuselage drag typically accounts for 30 to 50% of the aircraft zero lift drag, and this significant contribution underscores the importance of minimizing fuselage drag to achieve efficient flight. Design expectation for a low drag. One of the primary expectations recommended during the fuselage design process is to achieve low drag. If drag is low, power to move forward requirement will be low. As there is more drag, more power is required. As the drag minimizes, there is a less power requirement, which leads to an efficient flight. This is a fundamental goal alongside other considerations such as low weight, positive contribution to the lift generation, external symmetry, and safety against environmental hazards. Drag reduction through component enclosure. To effectively reduce aircraft drag, the fuselage is designed to enclose several other major components and systems. These typically include the landing gear, the engine, and the fuel system, and along with power transmission system. By housing these components within the fuselage, designers can create a smoother external profile, thereby minimizing foam drag and interference drag that would arise if these components were exposed. As all these components are housed inside this fuselage within the streamlined body, this becomes a smoother surface for the airflow, which will minimize the drag. The fuselage design is heavily influenced by the need to reduce drag. Its shape and ability to enclose various internal systems are critical to minimize aerodynamic resistance, which in turn contributes to the unmanned air vehicle's performance and efficiency. The fuselage of an unmanned air vehicle can play a role in lift generation, although its primary function is to house the payload and autopilot mechanism. Design expectation for positive contribution. One of the key expectations recommended during the fuselage design process is a positive contribution to the lift generation. This implies that designers aim for the fuselage to actively help in producing lift rather than merely acting as a housing structure. Potential for significant lift contribution. The fuselage may be aerodynamically designed such that it provides as much as 20% of the total lift of the aircraft. This highlights the potential for the fuselage to be a notable contributor to the overall aerodynamic lift. Typical lift contribution in basic configuration. In a basic configuration, however, the fuselage typically produces only about 5% of the aircraft's total lift. This suggests that while there is a potential for higher contribution, a standard design might see a more modest role in lift generation. While the fuselage main purpose is accommodation and housing, its aerodynamic shape can be optimized to contribute positively to the aircraft's overall lift, potentially providing a substantial portion of it when specifically designed for that purpose. The main fuselage or nacelle structure in most aircraft is typically elongated in the direction of flight, suitably streamlined and designed with means of access to the interior. The primary purpose of this structure is to provide space for housing the numerous components required for flight control and payload operation. When designing and constructing fuselage structures, key considerations include the desire for lightweight, high strength, and good rigidity. Common construction materials include plywood, carbon fiber, reinforced plastic, rigid foam, polymers. This is a nylon engine nacelle and fuselage and interior structure. This is the nacelle and fuselage interior structure of nylon material. There are various internal structures which you can see here in order to provide rigidity support so that it is not broken during the flight due to the gust loads. Construction methods. Aircraft fuselage construction has utilized various methods including space frame and monocoque techniques. Currently, there is a preference for using selective laser sintered printed nylon monocoques, while SLS nylon has an inferior strength to weight ratio when compared to CFRP. It allows for the adoption of complex geometrical reinforcing which can lead to competitive structures. A significant advantage of 3D printed structures like SLS nylon monocoques is they do not require molds or other tooling for their construction. They also facilitate the easy inculcation of fittings for bayonets, hatches, switchgear and sensors. These are the bayonet systems for access to internal avionics and fuselage mounted switch and voltage indicators. This A bit is showing about, picture A is showing about bayonet system for access to internal avionics, and this picture B is fuselage mounted switch and voltage indicators. Here this is the voltage indicators and this is the switch. Use of rigid foams. When very light structures are needed, the use of rigid foams can be an attractive option. However, when using foam and sometimes nylon or even some CFRP structures, special care has to be taken to provide hard points for fitting highly loaded components like engines or undercarriage. This typically involves gluing load spreading plates made from thin sheets of plywood or plastic to the foam. Despite this, foam can be used for the entire structure of lightweight design. This is commercially produced model aircraft with foam fuselage. This is in many cases we have seen the students making their models using foam boards and fluke boards. They trim it accordingly, according to the shape of the fuselage or according to the sizes of the wing, depending upon the airfoil configurations. Combining attributes of different materials. One effective way to combine the benefits of CFRP, foam and SLS nylon is through a foam covered space frame. This type of structure is typically made of CFRP tubes joined together with SLS nylon clamps. This demonstrates its versatility as a joining component within hybrid structures. Space frame structure made of CFRP tubes with SLS nylon joints and foam cladding. You can see here the tubes. These are the tubes. And this is the foam cladding. This part is foam cladding. Integration of fittings. SLS nylon structures facilitate the easy inclusion of fittings for various components such as bayonets, hatches, switchgear and sensors. This case of integration is crucial for the functionality and assembly of aircraft. Need of hard points. Hard points are generally needed to mount the power systems. When SLS nylon is used for the main fuselage material, it may be necessary to provide hard points. This is similar to rigid foam structures where load spreading plates, often made from thin sheets of plywood or plastic, are glued to the material to accommodate highly loaded components like engines or undercarriages. For highly loaded components such as engines or undercarriage, special considerations are necessary to ensure secure attachment. This is particularly true when constructing fuselages with very light structures using materials like rigid foams. In such cases, special care has to be taken to provide hard points. These hard points serve as reinforced areas designed to withstand the concentrated forces from these heavy or dynamically stretched components. The need for hard points is not limited to foam structures. It can also be necessary when using nylon for the main fuselage material. Even some carbon fiber reinforced plastic structures incorporate metal hard points within their molding process, indicating that this is a common practice for integrating high load components across different material types. Conclusion for the lecture. The unmanned air vehicle fuselage plays a crucial role in influencing aerodynamic performance, being one of the three primary components of an unmanned air vehicle structure. Its main purpose is to house the payload and autopilot system, making it central to both operational capability and mission effectiveness. Payloads vary based on UAV type, ranging from sensors and communication devices in non-military unmanned air vehicles to weapons like rockets and bombs in military UAVs. These are the references used in the lecture. Thank you. We'll meet in the next lecture.